In this example problem, we have a metal bar that has a weight of 200 newtons and a length of 4 meters that is hung horizontally. So that's what I've drawn here, is this bar that is horizontal. And one of the bar is attached to a hinge on the wall, while the other is attached to a wire. So we've got our hinge sitting here, we've got our wire attached here, and the wire runs from the bar up to the wall. And the angle in here is 35 degrees. And then there's a sign here that has a mass of 10 kilograms and a length of 2 meters that is hung from the end of the bar near the wire. And we want to know what the tension in this wire here is. So when I look at this, I have a whole range of forces. I have a force normal here from the hinge. I have the weight of the bar itself. I have the weight of the sign, and I have the tension. And the problem is I have the weight of the bar and the weight of the sign, because I know the mass, so I can multiply by 9.8 to get the weight. But I don't know what the tension is, that's my unknown, and I don't know what the force normal is. So I can't sum forces initially in order to solve this. This means that I am going to sum torques instead. So for step 1 of this process, I'm going to sum torques on the metal horizontal bar. And so I've labeled all my forces, so I have a force normal and I'll have a y component and an x component here. I have my tension, and my tension is going to have both an x and y component because it acts at an angle of 35 degrees. And the part I'm worried about is what touches here at the end of the bar. I have my weight that is going to act at the center of the bar, and then I have the weight of the sign that is going to act at the center of the sign. So since I don't know force normal and I don't want to find it, I'm going to set R equals 0 on the left end of the metal rod so that I can then find the force due to tension that is acting on the other end. So I have 4 torques: the force normal torque, the one from the weight of the board, one from the weight of the sign, and one from the tension in the rope. My torque normal is going to be 0 because F times R in this case would be 0 because R is 0. And then I have the weight of the bar times the lever arm for the bar, plus the force for the sign, and then the lever arm for the sign, and then the force from the tension. We have to be careful with this one, we're going to have to break this one into components, and then the lever arm for the tension. So I'm given directly the weight of the bar, and the lever arm is going to be 2 meters because the bar is 4 meters long, so from the center to the left side would be 2 meters. And it's going to be negative because if we're imagining it rotating around here, this rotation here, so going down this way, is clockwise. Next we are going to deal with the sign. Now the sign, you're given the mass, so we have to multiply by 9.8 to get the weight in here. And then the sign is 2 meters long, and it's at the one end of the bar closest to the wire here. So we're going to apply the weight of the sign at the center of the sign, since it's also a homogeneous symmetric object. So the sign is 2 meters long, so at the 1 meter mark of the sign, you would apply the force due to gravity. So it's 2 meters here, and then another meter here, so the lever arm is going to be 3 meters. And this torque is also going to be negative because the weight once again pulls down this way, so this is clockwise, so this is also going to be negative. Our last torque is due to the force due to tension, and you have to remember that only perpendicular forces to the lever arm cause a torque. So that means we need only the y component of this force due to the tension. That's the only component that's going to cause a torque. The x component will not. So I multiplied the magnitude of the force times the sine of 35 degrees in order to insert just the y component there. And the lever arm is going to be 4 meters because the wire acts at one end, where 0 is set at the other end of the bar. So since the length of the bar is 4 meters, the lever arm is going to be 4 meters. And since the wire is pulling up and to the left, up means going up and around. Remember, this is our rotation point. So that is counterclockwise, which is why we get a positive sign here. So when we solve for the force of detention, we get 302 newtons.